Okay, welcome to the post-lunch talks. We're going to get the general track started in just a moment. And to start us off with the first talk in this session, we're going to hear about Numba v2 towards super optimizing Python compilers with Kwan. So thanks very much, and take it away.
Thank you. Hello, everyone. My name is Sue. I work with Anaconda, and I've been working on Numba, a Python compiler, for more than a decade now. So before we start, my boss asked me to put this disclaimer on because what I am about to show may sound a little bit crazy, but I will show how actually this is all practical. And that despite I'm talking about Numba v2 is more like a code name. The current Numba version, the so-called v1, is going to be supported, and we have many planned releases. The new project that we are describing here is not available as a ready-to-use library, but we have a set of demos, and there are a Jupyter book at the end, which I will show. You can check out and have a look. And stability is very high priority for us, so new components of v2 will be added to existing versions of Numba when it's appropriate. So we're doing the crazy stuff in isolation. So I don't know if everyone here is familiar with Numba v1. And so to recap, and to put it simply, it is a optimizing Python compiler. And it does most of the work by translating bytecode, Python bytecode, into LLVM. And doing so is to turn the bytecode into a machine-level format that LLVM likes. So we give LLVM something that looks like C or Fortran. That's the LLVM is doing most of the optimization. For us, Numba developers, we have been thinking, like, how can we make it even better? How can we do something that LLVM cannot? And LLVM is an awesome project. So having worked with the community for 10 plus years, helping community write optimized Python code, we realized that optimization is hard. When I say optimization, I'm not talking about machine learning optimization. I'm talking about getting your code to run fast. We want your code to run very efficiently, but Numba being very limited in the current version, we have to basically ask people to write it as if you were writing Fortran code. Then you kind of get close to the machine level, and LLVM can do a very good job on it. But what if, in the future, we can actually get to a compiler that can explore all possible optimization for you? And once you have all this optimization, how do you know it is good? Right now, today, all the tools requires you to do performance evaluation on your code, benchmark. This is tedious. I don't know anyone actually liked writing benchmark. And benchmarking has many pitfalls. Like, how do you even know if your benchmark is any good? And is it actually representative of the real workload? So what if the compiler also help you determine what is the best optimization? That's how we get to SuperOptimizer. SuperOptimizer means it's a compiler that explores all possible program rewrites and extract the best program for you. By rewrite, I mean you can have two equivalence expressions, like the example I show there, is based on matrix associativity on multiplications. So left associative is the same as right associative, minus IEEE 754. So you can, this is kind of an example of the rewrite, and we will talk more about that. So the way we achieve super optimization is with a technique called equality saturation. This has been something that has been very popular in compiler and language programming theory. In traditional compilers, they are heuristic-based. You have, like if you have GCC, Clang, LLVM, they have pre-canned passes, O1, O2, O3. You always run the same set of passes. And this is basically a straight line, more or less. In the equality saturation, your compiler becomes a search. Given a set of rewrite rules, it would try to find, by deriving variation of your program using these rules, and kind of explore the entire space of your program following this equivalent semantics. And then at the end, you can get the best one by evaluating all of them. That sounds a little bit crazy, right? So there will be a lot of demos, the two main ones. And for the compiler engineers listening, here's the obligatory compiler pipeline diagram. And the pipeline can be just thought of as very simple. It's a Python AST front end. The analysis and super optimization is the back end. And at the end, instead of generating machine code, I want to highlight how useful super optimization is. So we are just going to get Python source code back. So the runtime will be the same for before and after, no machine code. And let me know if this is too small. So the first, okay. There will be a lot of graphs, so you don't have to read the small words. The first demo is the associativity rule for matrix multiplication. So this is basically what we are looking at. Oh, it's getting smaller. So everybody knows this. The math identity associativity, A times B times C, if you can group it either A times B first and then times C, or A times B, C together. By math identity, they are identical. In real life, float is not real. But if you can use fast math, then you can do this. And why is this blank? OK, there you go. OK. So the associativity rule holds for the result, but the performance of these two equations is not the same. If you compute the cost for these operations, matrix multiplication, you can use for BLAS convention, the 2m and k, basically product of all the dimensions times 2 is the number of operations on the processor that you need. If you compare the left associative cost and the right associative cost, you see that for the shape that we have, the shape here is the m and k. The right associative one is about 10 times less costly. That's only, that doesn't count memory cost. If we do a quick benchmark, we see that, oh, for our case, right associativity one would give us 1.5x speed up, just by putting a parentheses in a different place. So what if we take this example and scale it up? That now we have 5 multiplications, and there are even common subexpressions. So this is what I'm talking about. 4 matrices, 5 multiplications. You can either write it just as is, just a sequence of multiplications. Python would default to use left associative. That's how its evaluation order goes. And if you were me, the first time I look at it, I would say, oh, I'm going to take the common subexpression out, and then the shape is similar to the previous one, so the rest of the things goes by right associativity rule. And you can kind of see the expression graph here. In case, because of time, I'm going to jump ahead. Right, with this rewrite that I've handwritten, you can get 5x speed up. And all you did is kind of reorganize these operations. But is this the best? How do we know if it is the best? So this is where super optimization comes in. We want to explore all the combinations. And for binary operations, you can calculate the number of combinations by using the Catalan number, which I've printed out a table for it. For 5 operations, 5 binary operations, there are 42 combinations. And you can kind of see how this number grows really quickly. You do not want to do it by hand. So how do we make the compiler understand the associativity rule? There's a package called egglog that does equality saturation and has a Python binding. And in it, all we need to say is, oh, the associativity rule is this one statement. Or if you see a map mode in kind of left associative form, rewrite it to the right associative form. And you can visualize it as formal logic. And you can look at it, they actually look very close in how the API looks like and how mathematic formal logic looks like. So that's great. We added a rule. Once we added the rule to the compiler, to the super optimizer, It will go into this data structure called eGraph, which I would explain more later. And the same path will run over and over again until it saturates. That's where the equality saturation comes in. That means the path can no longer apply, and you can no longer grow the graph. So after you do that, you have many versions of your program. You need to extract the best one. So we can use our cost model from earlier, the 2 times n times n times k. And I highlighted here, this is all you have to do, just input the equations. Where do we get mn and k? Numba does shape inference along with the eGraph saturations. So it has computed that for you. You just put in the equation, and at the end, you can extract the Python source code. In practice, we get MLIR, but for demonstration of superoptimization, we are just going to get the Python source code, and you can see this is the extracted source code. It's hard to read, so you can look at the graph here. So the left-hand side one, the picture is the original. The middle one is my hand-tuned version. The right-hand side one is the super-optimized one. They are different. The right-hand side one, the super-optimized one, actually didn't use the common sub-expression trick. And this is not something that I would have guessed. And turns out, just by reorganizing these operations, there's a 15x speed difference. And I don't know about our audience, I've never considered something so trivial to have that much speed difference. Remember, no machine code. It is running on the same Python runtime in same NumPy. So just reorganizing your source code. So what I've shown is a better way to optimize code. You can write rules that are decorative, and they're actually composable. They are pure logic statements. They have no side effects. It can run in any order, and that means there's no phase ordering problem. That you don't have to care about the ordering of your compiler passes. And this rule will run repeatedly, recursively, exploring all the combinations for the simple equations that we have. When I evaluate this program, I try to grid search over all the matrix, a bunch of matrix sizes, so 64 of them, and it turns out the super optimizer would get you 6 variants to cover a large range of matrix sizes. And with these 6 variants, you get an average of 2.25x speed up, and 90% of cases get a better result, but I mean faster code, even though our cost model is extremely simplistic, just at 2mnk. Imagine what we can do with better cost model. The next demo is from a paper called Tensor. It's a state-of-the-art super optimizer for deep learning tensor graph. So they have some rules that I'm going to use, and there is a sibling paper, there's Tensor, which use equality saturation to implement the same thing. So over here, I'm going to run the notebook. So in this case, another simple example to illustrate. So we have a tensor equation is A times parentheses B plus C, and then times D. I don't know if anyone knows, you can actually rewrite A times B plus C times D matrices into using concatenation. If you could use if you horizontally stack A and C, and then vertically stack B and D, times them together is the same as the equation on the left. So this is a rule from Tensor. I used it into our original equation, and of course, in order to use this, we need a distributive rule. And so the original equation is this, and my handwritten version is this one. We have the shape of our matrices. Let's skip ahead to, now we want the optimizer, super optimizer to learn about these rules. So we just have to spell these 3 rules. The tensor rule, which turns the add into H stack, B stack. The distributive rule, one for the left-hand side, one for the right-hand side of distributing the terms. And you can also, again, see the formal logic for them. Then we again, update our cost model. We add the H-stack, V-stack. This time, because we're estimating flops, I just put something random in so that it gets OK-ish answer. But that's good enough for the demo. And then at the end, we run the pipeline, we extract the results. Oops. By the way, all these demos are available at the end. I'll give you a QR code to find all of these. So I can skip ahead. Again, these are the 3 expressions that we got. The original one on the left, the hand-tuned one in the middle. The right-hand side is the super-optimized one. They are all different, and you can look at the benchmark. The super-optimized one gets almost 10x faster. Again, no machine code was generated. All we did is reorganize the Python source code and using the H-stack, V-stack trick. And notice the hand-optimized one is actually worse, or actually almost the same. So this kind of optimization can get really tricky. It's really dependent on your application and your domain, the shape of your data. So after this, I also did evaluations, grid search over matrix sizes, and the super optimizer would get you these 3 variants. This time, however, it doesn't always give you a better result. The mean is almost 1, but there are extreme cases where it can get to 50x. And that is the cases where it's deep learning, when you have tall, skinny matrices, which is expected given where these rules came from. So diving into the technical details. We didn't build Numba V2 just because it's cool and sounds crazy. It's out of necessity. Numba V1 has been suffering from a lot of problems. The phase ordering problem, which is the pass ordering problem, is a well-known problem with compilers. And for us to compile Python, that is even harder. Because Python is highly dynamic, we find that in order to handle very dynamic Python functions, we have to interleave type inference and inlining and fix point over it. Sometimes we just don't even know what that pass ordering is in order for it to work. Numba currently has some sort of backtracking into it, but that's very slow. Equality saturation actually would solve this problem. Another thing is we want to help domain experts to contribute to the compiler. Like the domain experts have been asking if they can put their own optimization into Numba, into the compiler, for their classes, for their array implementation, for their data frame implementation. So we want, by not having phase ordering problem, the passes can go anywhere. By having these decorative, composable, logical rules, we think it becomes easier for people to write these optimizations, as there's no side effects to them. Finally, we want to get to tensor optimizations, because that's all the rage these days. We don't want to build a tensor optimizer just for tensors. We want a general purpose compiler that can do tensor optimization. And dgraph helps, equality saturation helps, and we also, which is not the focus of this talk, we have a higher level program representation that allow us to, at the same time, encode general purpose Python with data flow-like constructs that is needed for tensor graphs. So I have talked about egraph that is needed for equality saturation. So what is that really? It's a data structure that's optimized. It's optimized for storing equivalent stuff. For us, they are equivalent programs. So the graph on the picture on the left is the initial egraph for the demo 2. And you see, maybe it's a bit hard to see, but there are actually color boxes, hues surrounding the nodes. They indicate equivalent terms. So everything, all the nodes within each colored box, they are the same, they have the same semantic, or they are observationally equivalent. At the end, once it's saturated, the graph will grow to the one on the right. So that's how the equality saturation works. And once the egraph grows to something very big, we have many copies and variants of the program, then we need to extract the final result, the one that is optimal. within each of those color groups is a E-class, and E-class have nodes. Each node is an expression. For example, in the E-class C, like you can say integer times 2 is the same as integer left shift bitwise by 1. You can do that trick, and the bit shift may be less costly. And so we want to choose all the best ones. We use the equality saturation for things like type inference, shape inference, loop analysis, and optimization rewrites. And actually, all these E-graph and equality saturations, they are very powerful. They actually come from set solvers and automatic theorem provers. So you can imagine you can do a lot of things with them. But they do come with risk. So saturations, as the graph grow, and if you remember the table of Catalan numbers, it can actually easily eat up all your memory. For extractions, it's actually like a traveling salesman problem. It's NP-hard optimization problem. But for us, we can actually easily de-risk it. The only essential path for us is type inference, which doesn't grow the E-graph exponentially, because every expression that you have in the program only has one type, and you cannot say two random types are equal. It's illogical. So if that's the only thing that we need to get machine code, we don't worry about blowing up the memory. And the only thing that the only other passes that requires more or less the saturation part is optimization, and you can actually time limit that because you are just doing optimization. So it kind of translates to those 01, 02, 03, becomes you run optimizations for 1 second, 5 seconds, or maybe a day, depending on how big your program is. But so far, what I've seen is it usually it's done in milliseconds for our relatively small programs. Extraction is the same. You can use iterative methods to approximate the solution for traveling salesman-like problems. Again, it becomes a time budget problem. And you only need it. The more you run, the longer you run, the better the results. So in the future, we are going to be going away from the flop estimation. We are looking at actually ND vector cost, because we need to consider compute time, memory cost, which is really weird. They are non-local. They have a cache effect. Even things like energy cost and floating point accuracy. This is where we may need to turn to machine learning to learn the cost model from profile data. And we also want to see how we can enable the community to contribute these optimization rules. Like imagine a future where instead of manually optimizing your program benchmarking, you can just download someone else's optimization rule that is in a similar domain that you are in, and the compiler will do it for you. But one of the open questions that we have is this kind of decorative logic programming, it may not be the most intuitive API for Python programmers. So that's something that we have to see and how we can solve it. And lastly, I want to highlight, like, why did I show all these math rewrites for compilers? Like, why is this necessary? So it turns out the PyTorch folks have this FlashAttention 2 paper, and if you know LLM, attention is a very costly operation. So they figured out this online softmax that needs to fuse into matrix multiplication to be optimal. And it turns out the author responded to one of the reviews saying that compiler can generally do fusion, but optimization requires numerical stability, and doing math rewrite is very hard. So in the future, in the next 6 months, we'll be trying to implement Llama 3 with this Python and NumPy using our optimizer and see if we can reach the holy grail of optimization. So like, can we actually derive the FlashAttention given rewrite rules? Can something so novel be emerged from some non-specific rules? So that's where we're trying to go. And thank you for your time. And as I promised, there's a QR code we should have what I call the baby dragon book. It's a compiler book with Jupyter Notebook you can look at and run, download. There's 9 chapters. Every chapter is a compiler that built from the previous chapters. So check it out. And I'm open for questions.
Excellent. I really love the Baby Dragon book. That sounds great. Okay, so as we've been doing so far, if you have questions, please drop them in reply to the questions thread on the Track General channel on Track. So we have 2 so far. So we have one question from Gil. In the demo, several different reduction and transformation rules are specified as individual sequential yield statements in a generator. How sensitive is the execution performance to the ordering of the different reduction rules?
Those are just a syntactical thing for egglog, the Python binding. They actually have no ordering to them. All the rules are, there's no phase ordering problem. It runs in any order as long as it matches.
Okay. And then we also have another question from Ken Williams. Okay, how does this work, especially with regards to the matrix operations, with compare relate to other packages like Laplace or BLAS that can be accessed behind the scenes from Python?
Right. So right now, I've only showed the Python level by reorganizing these operations. But once we, like using LAPACK and BLAS, it's more like a lower level optimization. When we get to MLIR, the actual backend would be doing that kind of work. But if you really want to, you can also specify a rule just to manually call into LAPACK. That's possible.
Okay, excellent. All right, and then we have another question from Jason. Will these optimizations be enabled by default when a user tries to compile a series of matrix multiplications?
Oh, so the way we think about it is you pick your own set of rules, depending on the domain. Because not everyone, like if you're in machine learning, you can tolerate some floating point errors. If you're in nuclear thermal monitoring, you don't want to do that. So it kind of be very domain specific, and you want to kind of install what you would need and try things out.
Yeah, okay, so you get control on that level.
Yes.
Yeah. Oops, sorry, my screen went to sleep. All right, and then we also have another question from Ryan. Is there a TLDR on the difference in capability between, for example, torch.compile and Numba v2? His understanding is that torch compile can compile NumPy code right now, but the control flow is tricky to handle.
Okay, I don't know of a TLDR, but we actually have a new way to handle control flow. As I alluded to, we have a higher level IR that is a data-orientated IR that makes control flow implicit. That kind of makes control flow easier to handle. And that's based on a PhD dissertation that's relatively new in terms of compiler years. Yeah.
Okay, excellent. All right, so going once, going twice. All right, we don't usually do too much follow-up, but Ryan snuck it in there. Is there an exportable artifact for Numba v2 compiled programs?
Right. In the actual backend, it emits MLIR, and then you get your typical executable that way. In the book, we didn't spend too much time doing that because it's just prototypes in the book. But you will see by chapter 7, it uses the MLIR backend.
And then Gil dropped in the chat that eGraphs are awesome. If folks are interested in learning more, there's a good resource, and he links it there. Yes. And yeah, from just this talk alone, I'm kind of in agreement. So, all right, let's thank our speaker once again.